Okay, so now we know what a differential cryptanalysis is. Let's see how we can apply it on a block cipher. And as an example, I will use the present block cipher because the structure is really simple. Recall that the block size is 64 bits. Each line here represents a single bit. Key length can be 80 or 128 bits, but the round keys are 64 bit again. So they are simple XOR operation here, bitwise XOR operation. Then there is a single S box. Okay, it is represented here and it is repeated 16 times in parallel. Then the places of the bits changes. So question is how the differential cryptanalysis applies to this design. So assume that I have a plain text here. So I encrypt it. Then I simply flip one of the bits here. So flipping one bit here, how it affects the layers. Recall that we had 3 layers: key addition, substitution, and permutation. Okay, and we will see that the only confusion layer is here, which is the nonlinear part, and actually only the problem for the attacker will be these S boxes. The other parts will be simple. So let's see. Assume that we are encrypting two inputs, I and I prime, with difference I XOR I prime is alpha. So alpha is the difference you introduce. So alpha can be 00001, which means that you are simply flipping the rightmost bit. Okay. Generally, we represent it in terms of XOR operations because this way we can follow what happens if you perform other XOR operations. So consider the effects of key addition, substitution, and permutation layers. So at the key addition, what we do is as follows. So don't forget that now we have two inputs, okay, two different plain texts. So we have to look at them in parallel and see what happens. So on one side, at the key XOR layer, you are XORing input with the round key. Since we are encrypting with the same key, the other plain text or input I prime will also be XORed with the same secret key, right, round key. Since both inputs are encrypted with the same key, their difference is still the same. So after this layer, the output will be this on one side. For this plain text, the output will be this, right? But if you XOR both of them, K's cancel each other since it is simply as an XOR operation, and XOR is just addition modulo 2. We end up with I XOR I prime, which is still alpha. So this means that if you have an input here and flipped one bit, and you have another input, if you add round key to both of them, at the start of this S box layer, we don't know these inputs, but we still know that their XOR is alpha. This is what we are saying. So, because since I don't know the secret key, I cannot know what the inputs of these S boxes are, right? But I can follow what the difference is, how it changes, and alpha doesn't change here after this operation. So question is, what happens after the S box layer? So we don't know the exact values of Si XOR K and Si prime XOR K because we don't know the K, right? Since I don't know the input, I cannot calculate the output of these S boxes. So we cannot exactly know the difference after these S box operations like this. But we can analyze the S box to see which input differences provide which output differences. And here how the differential cryptanalysis applies. This is the only part you actually have security against differential cryptanalysis, and you have to analyze the S box to see what happens. Okay, so with some probability, you can say that the output difference will be this or that. Okay, this is the idea. Before moving on to that, let's focus on the permutation layer. Presence permutation layer only changes the places of the bits, right? So if the input has a non-zero difference at the ith bit, then the output has a non-zero difference at the pith bit, where p is the permutation. Here, what we are saying is that assume that you flip this bit, right? So this is the difference. So let's focus on the difference. The difference is that all 0 and 1 bits. After the key addition layer, you add the key to both of them. So the output difference are still the same, all 0 here and 1 here. This is not the input to the S box. This is the XOR of these two inputs. So after these S boxes, the output will be still 0 because if you put the same input to the S box, the output will be same. But only difference is here at this point because one of them has an input, the other one is just the same input with this bit flip, right? So after the S box operation, some of these bits will have non-zero difference. So, and those non-zero differences, if it is on this bit, it will stay here. So in the next round, it will be here. But if it is here, it will go here and go here. So I can still follow what happens. But the only problem is that just focus on a single S box. I'm putting it a random input. For instance, let's say B. Input is B and the output is A. Question is, what happens if I simply change one bit? Okay. Since I know the input, when I flip the bits, I can know what the output will be. But if I don't know the input, what happens if I simply change one bit? So look at this example. Assume that the input was 0. If I'm flipping the rightmost bits, the output will change from C to 5. But if the input is 2, and I flip one rightmost bit, it will be 3. So the output will change from 6 to B. Okay? This way, 9 will go 0, A will become D. So you can see what I'm going with this, right? If I introduce a difference, I'm looking at what kind of differences I observe. So in order to do this, we have a way of calculating the probabilities, and this is called DDT, difference distribution table. An idea is as follows. Consider every possible XY input pairs of a single S box. Okay, so these are 4-bit values. And introduce the difference I so that X XOR Y equals to I. And count the output differences where X XOR SY equals to J. Okay, so you are putting an input difference to, sorry, you are introducing a difference to input, and you are looking at the differences of the outputs. Construct the table with this count as the ijth entry. So the result for the present will be this table. Okay. So let's see what this table means. So if the input difference is 4, this table says that output difference is 5 with probability 4/16. So 4 out of 16 times, if you introduce the input difference 4, the output difference will be 5. So actually this comes from this table. So since if the input difference is 4, you looked at the row 4, you go here, and you realize that there is 4 here at the 5th column. So this means that 4 out of 16 cases, we have to see this difference. So what does this mean? So let's look at the S box and see how this works. So assume that your input is 0, right? So the output is C. If I introduce the difference 4 XOR 0 is 4. Now the output difference is 9. XOR 9 with C, you will see that it is 5. Okay, so since this is the case, initially I make all of this table all 0, but just by observing this, I increment this by 1. So when the XY pairs 0 and 4, I observed 5 outputs. But flip this, instead of choosing X equals to 0, choose X equals to 4. Then add the input difference 4, and 4 XOR 4 is 0. This is why you observe the same difference again. This is why all of the values here are even, because choosing XY and YX with the same difference will give you the same output difference. Okay. So this way, since I gave the example as 0 and 4, now move on to the next one. Take 1 and XOR it with 4, it is 5. So 1 goes to 5, 5 goes to 0. So 0 XOR 5, again is 5. This is why now this value is 4. But if you look at other values like 2 and XOR it 4, you get 6. So 6 and A, if you XOR them, it doesn't make 5, right? It does something else. Let me try to compute it. So I think it is C, right? If I'm not mistaken. Yeah, here you see, you observe C too many times. So this is how you statistically find what happens when you give an input difference. So when the cryptanalyst looks at it, they try to look at the largest values in this table. And they will going to exploit those things because this means that the probability is higher. Okay. So let me give an example with present, but before I will give some information about DDT. The highest values in the DDT except the first entry is called differential uniformity. By except the first entry, I mean this because if you introduce 0 difference, then the output also has 0 difference. This is why it is 16 and all zeros here. So instead of 4 by 4 S-box, if it were 8 by 8 S-box, this value will be 256, okay? So we don't care about this first row or first column, okay? So we focus on this part, and we try to look at the largest value in the remaining part, and that is called differential uniformity. High differential uniformity provides characteristics with high probability, hence lower is better for the designer, and higher is better for the attacker. Values in DDT are even because the pairs xy and yx provides the same difference. Thus, the theoretically best achievable differential uniformity is 2, right? Because the table can be filled with zeros and twos in the best case scenario. Otherwise, you will be some even values which are larger than 2. So for odd n, we can construct such n by n S boxes, I mean, with differential uniformity too. So you have a 5 by 5 S box where this table is filled with zeros and twos and nothing else. But the thing is that for n equals to 4, which is even, there is no such an S box. So this is why present doesn't have an S box which is 2 uniform, because there isn't such an S box for the case of 4. So this kind of led to the idea that there is no even n where you can have differential uniformity S2, because even AES has a very nice S box, 8 by 8 S box, but it is 4 differential uniform, not 2. So people thought that there isn't such an S box. But in 2010, Dylan found that 6 by 6 S box constructed in a very nice mathematical way, which is 2 uniform. So the big open problem is that, can you find a 2 uniform 8 by 8 S box? So an 8 by 8 S box, so that the DDT table here is filled with zeros and twos. So know that that S box will be more secure than AES S box. So, if you want to be famous in this area, this is the problem you need to solve. But as you can imagine, a lot of people tried and couldn't come up with a solution to this. So if you have a clever idea, just go for it. So presence S-box designs are some good designs, like good criteria, like they chose something differential 4 uniform. You can do something worse like 6 uniform or 8 uniform. They chose no fixed point. This means that the input x never goes to sx. So this means that if you go to s-box here, for instance, 0 never goes to 0, 1 doesn't go to 1. So there are no fixed points. These are sometimes important because we don't like fixed points in cryptography. Because if you choose a fixed point, then that layer for that input doesn't create any confusion, right? They also choose the S-box so that 1-bit input difference never provides a 1-bit output difference. Because if this is the case, you can find, high probability events. So by this, they also mean that if you look at the row with 1, this means that you are introducing the input difference 1. But as you can see, you never see the output difference 1, 2, 4, or 8, which are 1-bit differences. So this is a design criteria. So these are some good ways of designing an S-box. So by now that we have a DDT table, how can I use it and try to find a distinguisher for present? So here's an example. Here, attackers do the following thing. They say that, let's assume that we have 2 plain texts, but their XOR is only the difference as 4 in hexadecimal notation, corresponding to S boxes 0 and 3. So if you go back to picture, so you have a plain text, but you XOR it with something so that their difference is, here 0, like 0, 1, 0, 0. And for the third aspect, it is again input difference is 4, which means 0, 1, 0, 0. So all 0 differences, except there is a 1-bit difference here and 1-bit difference here. So question is, what happens after the S-box operation? Okay, the input difference is 4. So here they are saying that we are going to focus, when the output difference is 5. So now we have to go to the DDT table and see what is the probability of observing 5 output when the input is 4. But we already mentioned this from the table. Where is it? here. So when the input difference is 4, you observe 4 out of 16 times, which has probably 2 to the minus 2. Okay, but since you are giving this difference to 2 S boxes, this probability is observing it for a single S box. Now you want to also see this output in the second S box, so you have to multiply the probabilities, assuming that these are 2 independent events. So this means that with probability 2 to the minus 4, these input differences will lead to these output differences. After the permutation, there's no probabilities involved, just the bit places of the bits changes. So in the next round, you end up with non-zero differences at the S boxes 0 and 8, and this time the differences are 9. So again, you go to DDT table. Here the attacker says that I'm going to focus on the cases where the output difference is 4. They do it because they look at this row with 9. Okay, they look at the values the highest. As you can see, here you have 4, also E. They could choose E, but 4 is just 1 bit difference, so they stick to the 4. Okay. Again, this happens with probably 2 to the minus 2, and this happens with probably 2 to the minus 2, then permutation, then S box there, and so on. So they say that if I simply change the 2 bits of this plain text as the positions like this, after 4 rounds of encryption, we will again see the differences only at those places. As you can see, these are identical, with probability of the probabilities multiplied here. So it is 2 to the minus 18. Okay. So we call it iterative here because, as you can see, the input and output difference are identical. So you can take this table, put it below it, and say that now I have an 8-round distinguisher, saying that this input difference goes to that after 8 rounds of encryption, but now the probability will be 2 to the minus 36, which is square of this value. Okay, so if you assume that these probabilities are independent, then the 4-round characteristics hold with probability 2 to the minus 18. Input and output differences are the same, so we can put the same characteristic below to obtain 8-round characteristics with probability 2 to the minus 13, hence the name iterative. So in the literature, Wang found a 14-round attack on present. So they say that if you put the input differences at these bit places, after 14 rounds, you only see this difference at the output after 4 rounds, but with probability 2 to the minus 62. As you can see, which is a very low event, but still it is larger than 2 to the minus 64. Why I'm saying this? Because the block size is 64 bits. So, you know, for a random permutation, giving some input difference and looking some output difference, probability of observing it's 2 to the minus 64. This is equal to the rolling a dice and seeing the result with probability 1/6, okay? So your aim is to find the longest differential, which has probability larger than 2 to the minus b, which is the block size, okay? So they do this, and after 2 rounds, they see that these output differences become like this. So they attack 16 rounds like this, so they capture ciphertext which have only differences at these S boxes, you know, perform 2 rounds of decryption, but only guessing the round keys that affect these active S boxes. So they kind of try brute force attack on these round keys and, you know, break the system. So let me finalize with this. Attack procedure is as follows. You gather M plain text ciphertext pairs with the input difference this, and the question marks means that can be any difference out at those places after 16 rounds. Key guess, partially decrypt these pairs with every possible key bits of rounds 16 and 15 that correspond to S boxes with non-zero differences. Correct key should have the highest counter. Exhaustive search. Remaining key bits are obtained by exhaustive search at the end. So this way you can break 16 rounds of presence. But you know that it has 31 rounds, so it's resist to this technique, but you have to, you know, check every other technique. So, okay. I'm not going to talk about these details, but those attack actually some overlooks some properties, since it is theoretical attack and it is not applied. some of the claims they make actually doesn't work in practice. So this is why I always suggest that, perform the reduced version of the attack in practice to see if it works. So there are many theoretical attacks which doesn't work in practice, or which works a lot better in practice than theory. So this is why you have to, for instance, if you find an attack on 8-round AES, which requires, enormous amounts of time and memory, instead of, trying to perform it at 8 rounds, reduce it to like 4 rounds and see if it really works, if you're overlooking something or not.